In the previous video, we looked at a center of mass of a system of 2 particles. Here we're going to look at a system of n particles. And, so let us say we have a system of n particles. As you can see, an object consists of a large number of particles, and this is the center of mass of this particular object, and RCM, this particular vector, represents the position vector for the center of mass. Similarly, this particle m1, this particle 2, this particle mn, and we'll have a large number of particles, and each particle will have its position vector, r1 for particle 1, r2 for particle 2, so on and so forth. Right? So this is an n particle system. What will be the equation for the center of mass of this particular system? That is what we're going to try to look at over here. So we derive this equation for 2 particle system. RCM is m1 r1 plus m2 r2 upon m1 plus m2. Using the same logic, RCM for an n particle system will be m1 r1 plus m2 r2 plus mn rn upon m1 plus m2 plus mn. Right? So this equation will give us the position vector for of the n particle system. Right? This can be written as sigma mi ri I is equal to 1 to n divided by sigma of mi I is equal to 1 to n. Right? Now this can be written as sigma of mi ri I is equal to 1 to n, and the denominator sigma mi is the sum of the mass of all the particles, and that would mean this gives us the total mass of the entire system, right? So which I can represent by capital M, right? And therefore RCM becomes equal to 1 by m sigma mi ri, right? I of course is equal to 1 to n. So this is the equation I get for the position vector of center of mass, right? Now let us take a few cases in this case. Supposing, let us take the case 1 when m1 is equal to m2 is equal to mn, and let us say that is equal to m, right? In that case, RCM will become equal to, if I use this equation, 1 upon m, and if I put this in brackets, I'll get m r1 plus m r2 plus mn rn, and that will, I can take out m common, so I'll get m upon capital M r1 plus r2 plus rn. Okay. Now m upon m, this is the mass of one particle, this is total mass of the entire system, so that this ratio will give me the total number of particles. So this can be written as 1 upon n, where n is the total number of particles, r1 plus r2 plus rn, and which n can be written as sigma ri I is equal to 1 to n divided by n, right? So, and for the 2 particle system, this equation RCM will become equal to 1 upon 2 r1 plus r2, right? Okay, let us take condition 2. Condition 2 is what would happen if RCM is equal to 0. That means the center of mass is at the origin of the circle. So if I go back to this diagram, then this C is over here, is the origin, right? If that means this RCM becomes equal to 0. If that it becomes equal to 0, then I'll get sigma mi ri 1 by m is equal to 0, right? If I look at this particular equation, right, RCM is 1 upon m, sigma mr is equal to 0. If this is 0, mass cannot be 0, so sigma mr is equal to 0, and therefore I can write therefore sigma mi ri is equal to 0. And if I try to explain this in what this would mean, that the sum of the moments of the masses of the system about the center of mass is 0, right? This MIRI, this is M1 R1 plus M2 R2, which are moments, and the sum of all these moments about the center of the mass is equal to 0, right? That is what this sentence would mean. So we have derived the equation for the position vector of center of mass RCM 1 upon M sigma MIRI, and we have also looked at two conditions for this. In the next video, we will look at the Cartesian components of the center of mass. Thank you.